Okay, good evening, everyone. This is a short week. Remember, this coming Thursday is a holiday, no class. Yay for that. Um, However, you will have two quizzes over that weekend, two Chapter 10 quizzes. Okay, I'll talk more about that tomorrow night, but I know they're in Mom, but I'll talk about more of that tomorrow night. So I want to get started. In my email, I said tonight and tomorrow night would be super, super important. We'll cover about 40% of what's going to be in the Chapter 10 section of exam number 3. So going back to 10.2, we talked about what was called exponential graphs. And I did, for example, okay, I did something like y equals 3 to the x minus 2. And I suggested to you that the easiest way to do this right now is just simply build a table of values. Okay, and plug in some numbers. If x is 0, this becomes 1 minus 2, which is -1. If x is 1, this is 3 minus 2. If x is 2, this is 9 minus 2, which is 7. But then you always have to play with the negative numbers. If x is -1, then this is 1/3 minus 2, which is -1 2/3. And if x is -2, then this is 1/9 minus 2, which is -1 8/9. Now, you're more than welcome to do all this on your calculator. Okay, I think better in fractions than decimals, but if you guys get decimals, it doesn't matter. And the total accuracy of this isn't really critical either. But what you do need to do to show, okay, when you graph this, okay, we have 0, -1, which is right there. We have 1, 1, which is kind of like right there. 2, 7, which is way up there. So already we're seeing the shape of this. We have -1, -1 2/3. So about there. That's -1. We have -2 is -1 8/9, which is about there. Now notice this is -2. So this graph looks something like that. And if you're not careful, you're going to do this and it's wrong. Okay, that's totally wrong. What I'm expecting you to see here is paying attention. As x gets more negative, the answers stay negative, but they approach -2. Approach is the key word there. So as x keeps getting bigger and bigger negative, more and more negative, okay, these are approaching -2. And that major idea was called an asymptote, okay? And I expect you to draw it in as a dotted line, label it as y equals -2, okay? And then answer questions like the domain of this thing is either fancy R, which means all real numbers, because the domain is the x's and they go to -infinity and they go out here further, +infinity, or you could say -infinity, +infinity. Those two are synonymous. Those two symbols are math for every number on the x-axis. The range is a little bit trickier. The range means the y values, and the y values start at -2, but don't equal -2. So we use a parenthesis, and then the y values go up to +infinity, like that. Now, when I taught this, I did something like this. This is how I'm going to test you. A graph very similar to this. Now, the base might not be a 3. and it might not be shifted down 2. You might not have a -2 as an asymptote, might be +2 or something like that. But it will be pretty much like that. Okay, that's what I'm going to test. Unfortunately, or fortunately, mom's problems are a lot more difficult than this. So I want to show you what I expect you to do with mom. Okay, mom is concerned with the general form for an exponential. Y equals A times b to the x plus, I should say, plus or minus a k number. So for example, y equals 2 times 5 to the x power minus 3. What would that graph look like? Okay, well, we kind of know what the 3 does. It moves it down. And we kind of know that, so there's going to be an asymptote at y equals -3. We kind of know that, okay, based upon this work. But how is base 5 different than base 3? What's this 2 do in front of it? Okay, better. What if we had -2 times 5 to the x power minus 3? What does that -2 do to the graph? How does it change the graph in some way? What about y equals, let's go back to regular 2, but let's put a 1/5 in here. Whoops, to the x power minus 3. So what happens if your base number isn't a nice, pretty whole number, but your base number is a fraction? So a lot of the questions in section 10.2 in MOM are much more, I don't want to say difficult, but much more detailed than this question. So how are you going to do it? Well, here we go. In the past, I've talked about a program called Desmos. Okay, it's actually desmos.com. I've talked about it a little bit, but really haven't, forced you to use it, pushed you to use it, or anything like that. But tonight we will for just a few minutes. So I want to share my screen. Go here. I want to go to Desmos. Okay. Bingo. Can everyone see my Desmos screen? Is there anybody that can't see a grid on here? Okay. So over here on Desmos, notice I went to desmos.com. Actually, well, whatever. So you just type in your equation, y equals, and I'm going to say 2 parentheses, 3 raised to the x power. Now, to get a power here, the easiest way for me is with the shift 6, and it puts, that's an up caret. Above my 6 on my keyboard, there's that thing. So if I want 3 to the second power, I actually type 3 up caret 2. There's other ways. Desmos has its own graphing utility, but that's the quickie way. Okay.
Does this one have a keyboard? You can like a calculator on the side.
Yes, it does.
Oh, okay.
It does have that. You can keyboard down at the bottom, and you can pick your functions that you want to pick right down here too. So yeah.
I feel this way that'll be easier on the actual keyboard.
Okay, that's fine. I mean, that's cool that you're using it. -2. Enter. Oh, that's because it's 2 to the x. Dummy. Okay, there we go. Okay. So let me close my keyboard here. So I just graphed y equals 2 times 3 to the x power minus 2. And we can see that down here, there's an asymptote. The graph isn't really as accurate as I wish, but you have to know that it exists. And you can see the graph going like this. Well, what happens if I take the same graph? So I'm going to copy it just like you would in a Word document. I'm going to copy it, Control C, copy. I'm going to paste it down here, Control V, paste it. But I'm going to change that to a -2. So look what I did right here. It's the same exact function. Okay, same exact function, except the top one is a positive graph, the bottom one is a negative graph. Well, look what happened. And by the way, for those of you who are not sure, these are color coded. So the top one is red, so you can kind of see the red graph. And the bottom one is blue, so you can see the blue graph. So you can see that the negative just flipped the graph over. Well, let's go down to another one. I'm going to Control V, copy that, paste again, but I'm going to turn this into 0.5. I want to see what happens when my base number right here is a fraction. Okay, in these two, the base number was a whole number. Okay, so what happens when the base is a fraction? Look at this green one. Whoa, it flipped it over. In fact, let's delete this one. In fact, let's change this to a 0.3 just for fun. Okay, there. So when you had y equals 2 times 3 to the x, it was this red graph. Okay. So, and when you had y equals 2 times 0.3 to the x, it was this bluish, greenish graph, whatever that is, green one. So you should kind of be playing around with this to do your mom homework on a lot of those things that ask you to do matching. They gave you a picture of like 4 billion graphs and said, which graph is which formula? Well, just use Desmos to help you. One thing that you might want to do is, I notice number 3, I copied number 1 again. So 3 and 1 the same, and I'm going to get rid of number 2. So look what happened here. I'm going to change that x to a -x. So it's going to be y equals 2 times 3 to the -x. Okay, -x. Oops. -x. Come on, dummy. Oh, come on. Oh, because I wasn't up there. Well, I just screwed that one up. Come on. Maybe I'll use your function. Where'd it go? I want that to be -x. There we go. Hey, look what happened. Y equals 3 to the -x looks suspiciously like something we've seen before. And I'll show you what that was. Okay, Control, paste it in there. Remember I had 0.3? Whoa, look at that. You could barely even see it. 0.3, a fraction, okay, is this black one, went in here. But -x, 3 to the -x is also this. Now they're a little bit different because 0.3 isn't the reciprocal of 3, but they're close enough. So you guys should be playing with Desmos as you do mom. There's about 6 questions, okay, that ask you to match the graphs. So just have Desmos available to you. type them all in, see which ones they match. You should get 100% on your mom homework. Okay, let me switch back. So over here, if I wanted to graph y equals 3 to the negative x power, okay, I could build a table of values, but remember, what does a negative power do? It turns this to the reciprocal of the positive power. So these two are actually the same graph because we've studied this. A negative power forces us to do the reciprocal of the base number. So this graph and this graph would be identical. But you can play with these. You don't even have to know that. Just let Desmos do all your mom homework for the first few problems on section 10.2. Okay, try to get a feeling, if you can, for what happens, okay, when you change the K value, what happens to the asymptote, what happens when you change the multiplier in front. We call that the A value, from positive to negative, but I'm not going to go into great detail on that. That will be left for, you'll study that. You begin to study it in detail in Math 104. You'll study it in a lot of detail in 116, 121, 141. So I've just given you a little heads up now. They'll go into much more detail, much more than I want to at this time. That was 10.2. Okay. If you have questions, again, the entire week, even though we're off on Thursday and Friday and Saturday and Sunday, I'm going to be hanging around. I'll answer your questions. So please, do ask questions, but use Desmos on section 10.2 as best you can. Next. Excuse me. The other day in section 10.3, chapter 10.3, I introduced something called the definition of a logarithm. The definition of a logarithm. And I called it the Brabar Rule. Okay. That's because it's easier and more fun to say. But it's technically in math, it's the definition of what is a logarithm. And what I told you is a logarithm was a weird exponent. And in section 10.3, they had a lot of practice. If you had the log base B of A equals R. Okay, so if you start at the bar, that's log base B of A equals R. Okay, that is equivalent to, that's why I use the double-headed arrow, because it can change forwards and backwards. B to the R equals A. So this is called a logarithmic equation. Duh, because it's got a log in it. This is called an exponential equation. Again, duh, because it's got an exponent in it. So these two equations are the same as each other. If you're doing a problem and you've got this formula and you don't like it for some reason, you've reached a dead end, you can switch it to this. Okay, and maybe that'll give you a help or give you a hand to get out of the problem somehow. Or if you've got an exponential equation and you don't like it, it just is a dead end, you can't go anywhere, you switch it back to logarithms, and maybe that helps you. And right at the tail end of class, so I gave you this, okay, and that's a pretty fundamental rule. You need to know that rule. You have to know that. Then we practice things. Oh, wait a minute, time out. I made a big deal here. Okay, notice I said a logarithm is an exponent. So the logarithm is or equals the exponent. Notice the R here is the exponent, and it becomes the exponent of the exponential. And remember, I made a big deal about you have to say the word base, log base B. Okay, that's because the base of the logarithm is the base of the exponential. The base is the base, whether it's a log or an exponential. The logarithm equals the exponent, so there's the exponent, there's the exponent. Okay, so there's all these things. I also said the letters don't matter. They could have just as said in a math book, log base A of B equals C. They could have used ABC. Okay, and that's equivalent to A to the C power equals B. Okay, A to the C power equals B. A lot of people like to remember this pattern. A to the C power equals B. B to the R power equals A. B to the R power equals A. So instead of just flat memorization, seeing this kind of pattern helps some people. I don't care how you memorize it and how you know it, but this definition is critical. Whether you remember it with the letters of Brabar or ABC or some other way, doesn't matter to me. You just simply have to know it. Okay, it will become fundamental to a lot of what we're going to be doing both tonight and tomorrow night. Where are we going? Okay, so a quickie example would be something like log base x of 2, no, base x of 9 equals 2. Log base x of 9 equals 2. And I could say, okay, we'll solve that or find x. And you're going, I have no clue. Okay, because your calculator can't do base x. Your calculator can do base 2 and base 3 and base 7. Your calculator can do all that, but it can't do base x. So what do? Well, you convert it. Okay, you use this pattern. You say, oh, this is the same as x to the 2 equals 9. And now you go, well, I can do that. I can square root both sides and get x is worth, now technically plus or minus 3. A lot of you guys missed it on the chapter 9 quiz. When you use the square root to both sides, you have to input a plus or minus there. So several of you blew that on the quiz. I think there was some problem like x plus 3 quantity squared equals, I don't know, 25 or something like that. And when you square root both sides, which is good, you get x plus 3 because the square and the square root cancel, but it equals plus or minus 5. So you had to get the plus or minus because you got two answers for that problem. Remember, in general, a power of 2, x to the power of 2, has usually two answers. So anyway, here I said you should get plus or minus, but you reject it. And I haven't talked about it yet, so don't worry, I'm ahead of myself. The base can only be positive. The base here has a restriction. So in this case, x is only 3. But don't sweat that right now. Okay, we'll worry about that one later. So here's a great example of how to solve a logarithmic equation when you can't do it. So you switch it to an exponential equation and then figure out how to solve that. So I want to give you two real quick questions. Okay. And on these two questions, I want you to use no calculator. To the best of your ability, no calculator. Log base x minus 3 of 27 equals 3. See how you do that? That's number one. Okay. And number two, log base 3 of x plus 1 equals 2. So try that to the best of your ability with no calculator. So I took the first problem. I applied the definition, the Brabar rule. So I had x minus 3 raised to the 3 equals 27. Decided to cube root both sides. But remember, the only time we get plus or minus is when you square root both sides. So be careful. The only time you got plus or minus is when you square rooted both sides, but we cube rooted both sides. So the cube root of this is x minus 3. Cube root of 27 is 3. That's going off to your graph paper and just, or scratch paper, I'm sorry, and doing the cube root of 27, which is the cube root of 3 to the third power, and the cube root, the cube power cancel to just 3. Okay. Pause 1 second more. So again, if we apply the Brabar rule, this is going to be 3 to the 2 equals x plus 1. So 3 to the 2 equals x plus 1. That's 9, so that's 8, because we take away 1 from both sides, equals x. And you're done. That was it. Okay, and this is part of 10.3. Now, there was more that we did in 10.3. More that's on the homework, more that I'm going to do. But there's going to be, when we come to the test, or actually the mom quiz this weekend, there's going to be some that say, don't use your calculator. Now, I can't stop you, duh, okay? But we're expecting work that could be done without a calculator. So if you come up with 6.0000, I'm going to, well, you used your calculator, okay? Or 5.99999, you used your calculator somehow. The problems that say don't use your calculator are doable without it. Doable just by you thinking through some steps. So try those to the best of your ability. All right, I need to erase part of this board. Any questions about the Brabar rule or the definition, which is its real name, or any of these examples I've done? Okay. Now, you'll notice that each one of these problems was a logarithmic equation, and we couldn't do it, so we converted it to an exponential equation. That was easier to do. Well, now I'm going to give us some practice going backwards. I'm going to give you the exponential equation, and we're going to convert it back to a logarithmic equation and see what happens. To do that, this is going to get a little bit awkward because different people have different calculators. Okay. But one of the things we talked about last week is if you had log base, I don't know, 5 of something crazy, 18. Log base 5 of 18. Okay. Either your calculator can do that, which is great, or it can't. And if it can't, then there's something called the change of base formula. And this could be the log of 18 over the log of 5, or it could be the ln of 18 over the ln of 5. It could be either one of those. It doesn't matter. You're going to get the same answer. Okay. So the log base 5 of 18 can be changed into either one of these. And if your calculator doesn't have all the fancy buttons, it's okay. Every calculator can do these two. Whether you push the LN button or the LOG button, it doesn't matter. So take 1 second. If your calculator can do log base 5 of 18, great. But even if it can, just for practice, see if you can do the log of 18 divided by the log of 5 and the ln of 18 divided by the ln of 5, and see if all of these don't give me the same answer, just to make sure you're pushing buttons right on your calculator. So we'll pause while you play with each one of those for just a second. So using the fancy button on my calculator, I got that answer. And then coming back and figuring out what the log of 18 was, this, the log of 5, this, and dividing the two, I at least got the same answer. Now, if you didn't, we can talk about what buttons you're pushing or not pushing. Same thing, the ln of 18 became 2.89, something, the ln of 5, 1.6. But again, when I divided them out, they still became that answer. So this is a little bit to make sure you can do your calculator, you can use your calculator accurately and good. You're going to have to be able to do this stuff, guys. We're going to run into a lot of problems that look like this. Okay, weird bases, and you're going to have to somehow calculate them. Okay, any questions before I go on to do a problem? Okay, then try and solve these. You must use your calculator and round to 4 decimal places. So use your calculator, 4 decimal places. So number 1, 3 to the x equals 15. Number 2, 5 to the x plus 1 equals 99. And we'll do one more, but we'll make sure we have those going first. So work on those. Okay, so my thinking. I'm looking at this going, this is an exponential equation, 3 to the x power, exponential equation. I have no idea 3 what to what power. I know, for example, 3 to the second is 9, and I know that 3 to the third is 27. So I know this has to be somewhere between 2 and 3, but I have no clue what. So this is where we utilize our Brabar rule. This is B to the R equals A. That's what this is. B to the R equals A. Okay, so this becomes log base 3 of 15 equals X. Remember, the logarithm equals the exponent. Whatever was the exponent up here it equals the exponent down here. The logarithm equals the exponent. Okay. Well, now all of a sudden, that's something I could do on my calculator. Okay, we just talked about that. So log base 3 of 15. Okay, so I get 2.46497 is approximately X, but I said 4 decimal places. Okay, so that kicks us up 2.4650 would be 4 places. Remember the 7 rounds the 9 up, but the only place 9 can go is to 10. So 9 rounds to 10 and 1 carries over to there. So that would be the 4 decimal places. Is approximately X. All right, this one, same thing. Okay, again, it's exponential. I don't have a clue. I have no clue what this is. Okay, so I go log. The base is the same as the base. Base 5 here, base 5 down here, my logarithm. Of, okay, the 99, a logarithm equals the exponent. This is the exponent, so it equals the exponent. So we use our calculator, log base 5 of 99, whichever, however you do it. Maybe you have to split it, I don't know. And we get 2.855108 equals X plus 1. So we're going to take away 1 from both sides. And we can actually do that in our head, take away 1, take away 1. So this is going to be 1.80551. Actually, 55. 1, 2, 3. No, where did I get the O? Dummy. 8. Come on. 5, 5, 1. I was right the first time. Okay, so taking away 1, and I rounded it to 4 places at the same time. So 2 problems where I gave you the exponential. You had to convert it into logarithmic. Then you had to use your calculator one way or the other to get that weird logarithm, get a value for it somehow. And that was your answer. Here we had to do 1 extra step. So any questions on those 2? I have one more that's a little bit more difficult, and then we'll get on to some really, really new stuff. Really new stuff. Any questions about either of those? How we took this exponential equation, converted it into a logarithmic equation? Okay. Then 7 raised to 2x plus 3 equals 129. This is number 3. 7 raised to 2x plus 3 equals 129. Try that one. So again, I don't know anything about 7 raised to powers. About I know is 7 to the second power is 49, and that's not even close. So I'm just going to use my Brabar rule. This is log base 7 of 129 equals 2x plus 3. That's converting this exponential equation into a logarithmic equation. Okay, use my calculator. Log base 7 of 129. And I get 2.497449 whatever equals 2x plus 3. Now, if you recall, what I said was, even though the directions said around the answer to 4 decimal places, what I said near the tail end of the evening last week was you don't round until the very last step. To the best of your ability, you carry as many decimal places in your work as you can, and you only round your final answer. Okay? And I'm going to follow that rule always. I only will try to round my final answer. So there's my decimal. Now, mathematically, what am I going to do in algebra? Well, look at this. Whatever I'm going to do, I'm going to take away 3 from both sides. So your calculator can do that. Okay, so you take away 3. I've still got this 2.49 on my screen, so I just take away 3. And I have, okay, negative 0.5 something equals 2x. Now that's kind of important, because the real accuracy is in my calculator, not what I'm writing on the board. Okay, so 0.5, yeah, who cares? It's here on my calculator, because I know my next step is I'm going to divide by 2, and I may as well do that on my calculator. This saves me from having to input all kinds of stuff. So whatever's on my calculator, I'm going to sit there and divide by 2. Okay, and I get, let's see, no room. Okay, I get negative 0.251. I've rounded it to 4 places. It went 127, and I rounded it to 13. And I fully will allow you to do something like this on the test. In fact, once you get to here, this step right here, you can do the whole rest of the problem on your calculator. Once you show me this step, you show me, okay, I've done my calculator bit here. You can say, I take that answer, I'm going to take away 3, divide by 2. And whatever that is your answer. You don't even need to show me this junk. Okay. Questions? Okay. Now, from my perspective, what I showed you last week in section 10.3 was technically enough to have done these homework problems. But I know from experience that just because I gave you enough technical knowledge, that doesn't mean you had enough practice and enough practical knowledge. So I wanted to go over it again tonight. Uses of the Brabar rule. And we're going to use that Brabar rule throughout the rest of this chapter in places you've never seen it before. Okay. But I wanted to show you applications of it and how to use your calculator again and make sure you get it. Like I said, technically, I gave you everything you needed to know last week. But just because I taught it doesn't mean you learned it. So I had to go over it. I wanted to go over it again. All right, I need to erase the board. Any questions about anything I've done, any previous problem, anything you want me to redo or re-explain? Okay, I sent out an email and I wrote it up here. I don't know. Okay, back up. No, and I can't change it. Does this work? Wait a minute. Oh, let's try something. Hello. Ah, can you guys see that? That's one of the handouts that I asked you or suggested that you download, print out of from Canvas. These are called properties of logarithms. And what they are is nice. What they are is there's a glare, but what they show you is all of the things I'm going to talk about tonight, but they're printed up nice, pretty, and organized. And I stole this from a TA from 11 years ago. It's got his name down at the bottom. Okay. And he did a wonderful job, except for one error, which I'll show you. You see it right over here? Okay, I'll show you that to you. Don't worry about it. There's also another worksheet I asked you to download. We won't get to this other one tonight, I don't think. But this one says solving log and exponential equations. Okay, I promise you, you will have probably 6 questions on exam 3 that look exactly like these. Okay, exactly. So if you study this and my notes, then you should do fine on that area. You will have, hang on a minute. You don't need to see me. You will have probably 3 more like these. So I'm trying to show you everything you're going to get on the test. And then the mom will help you work on this. So I need to erase everything on the board. Again, anybody have anything they want to ask or have me show or tell a little bit clearer or slower before I erase? Okay.
Does this only work for log or can you do ln?
I'm going to cover that, but the answer is you could do ln because ln is a logarithm. Everything, I'll cover that. Hang on. If I haven't answered your question by the end of the evening, yell at me. That actually was a really cool, insightful question. All right. In chapter 10.4, we introduced something called the log laws. And there are some very basic laws. And then there are some more difficult logs. The single most important log is the Brabar, the log base B of R equals A can be converted into B to the A equals R. Okay, that's number 1, number uno for the basic rules. Then there's a bunch of other little ones. Now, don't take notes yet. I'm going to do some examples, and then I'm going to show you what the thing is. So we're going to have about 5 or 6 basic rules here. Okay, and I'll show you how they work, but don't mess up your notes yet. The first example I want to know is, what does log base B of B equal? What if we have the log of a base b of the same thing? For example, what if we had log base 5 of 5? Well, watch this. We know it equals something. We know it equals something. So if we then apply the Brabar rule, we have 5 to the x equals 5. What's the only thing x can be to make that problem true? 5 to what power equals 5? Doesn't x have to be worth 1? So here's the log law or log rule that I'm trying to figure out. I made an example. Log base 5 of 5 equals something. So I applied the Brabar rule, turned it exponential, and said, the only thing x raised to the first power has to be 5. But wait a minute, what if that's a fluke? What if I had log base 3 of 3? Well, that equals something. Why? I don't know. So apply the Brabar rule. 3 to the y equals 3. So what's the only thing that y can be worth so that 3 to the y is worth 3? It can only be worth 1. So based upon example, the log base b of b is always worth 1. Okay, so that's rule number 2. Log base b of b is worth 1. So, and that can be anything. That can be, for example, the log base 15 of 15. That's 1. If the base and that number are the same, the answer is 1 if it's a logarithm. Okay, another one. What if I had log base b of 1? What's it equal? And we'll do it again. We'll take an example. Log base 3 of 1. It equals something. It equals x. So apply the Brabar rule. This is 3 to the x equals 1. Based upon our knowledge of exponents, the only thing x can equal is 0. 3 to the 0 power is 1. Okay, fluke, maybe. Well, let's try something else. Log base 10 of 1. Log base 10 of 1. Well, I don't know, it equals y. So Brabar rule, 10 to the y equals 1. Again, the only thing that y can possibly be worth to make this problem true is 0. So it looks like we've come up with another log law. The log base b of 1 is worth 0. Okay. Some other ones that we've talked about. When we take the log of, let's say, x, you're supposed to know that that is the log base 10 of x. The base is implied to be a base 10. When I leave it off, okay, it's implied to be a base 10. And that's something you need to know. Okay. When we write the ln of x, again, we covered this the other day. The ln is a special kind of logarithm. It is the log base e of x. So there's a question was, do all of these log laws apply to ln's? Yeah, because ln's are just special logarithms. And I will do some more problems to reinforce that. ln's are logarithms. And by the way, I indicated that that handout had an error. Okay. Let's switch it over. Okay, I indicated, and I'll do this again tomorrow, but I said the handout has an error. Right there, he said the ln of m, whatever m is equal to the ln base e of m. Right there, okay? It should be log base e of m. So the second equation, he's got the ln of m, that is correct, equals log base e of m. That is incorrect. He wrote it wrong. Okay. So that's kind of what I used, only instead of capital M, I use an X, but it means the same thing. Oops, I'm pointing to the board and you guys can't see it. Good job, Foster. Yep. Excuse me. So this is exactly what he wrote on that little handout, except I used an X, he used a capital M. It's all the same. All right. Next one. We have our change of base formula. Log base B of R, whatever in the world those are, is the log of R. Oops, that's an R. Come on, dummy. Divided by the log. Come on, Foster. Of B. And the implication there is these are base 10. So you can change them into base 10 problems. So if you have log base 3, we just did this in our handouts. We just did log base 3 of 15 can be written as log of 15 over log of 3. And the implication, these are all base 10. Okay, change of base formula. I also indicated that you can write this as the ln of R over the ln of B, if you wish. It might be easier. Okay. And one more thing I want to put up here, and then we'll get to the intermediate laws. And this always flummoxes students. 3, this is 4, 5, this is 6. If I write the log of 10, if I write the log of 10 without your calculator, what's it worth and why? No calculator, just your brains. Okay. The log of 10, hang on, let me write this up. I'll give you the answer and then I'll erase all my work. The log of 10 is the same as the log base 10 of 10. Remember, because when we write log, it's implied to be base 10. But wait a minute. According to this rule here, the log base B of B is always 1. So the log base 10 of 10 is equal to 1. So the log of 10 is 1. Try that on your calculator. Log 10 equals 1. Your calculator, you put log 10, nothing else, you should get a 1. But you're getting it because of this, what I'm calling the basic rule. Now, super duper important. The ln of E. Remember, I introduced E as some magic number, 2.78 something or other, used quite a bit in social sciences, okay, or any science dealing with living things. Any biological science will use E. Somehow it'll show up. It always does. So without your calculator, what's the ln of E? Well, we go back to, what does ln stand for? Ln stands for the log base E, but this is of E. The ln of E, the ln of X, is the log base E of X. So the ln of E is the log base E of E. But by this rule here, that's still worth 1. So what we want to know is the ln of E is always worth 1. Now, if you can get your calculator to do that and check it, it'll be true. And those are some basic, and I mean basic log laws. We're going to go to intermediate ones in a second. Okay, does anyone need an explanation of any of these basic ones? You want more examples, or you want me to explain it? I don't know if I can explain it differently. I can certainly try.
Number 6 law for the log base R for the
B
red,
O-
what is that, 10 or is that
That's
B?
that's a 10. I'm sorry. That's me trying to squeeze in. When you write log of R, it's implied to be base 10 of R.
Okay, thank you.
It's still my crappy handwriting. No matter how I do it, I got bad handwriting here. Anybody else? Okay. Then I'm going to erase 7 and 8 because I want to, these are actually implications of combining these laws. So for example, if we took rule 5 and use it with rule 2, that's how we got number 8. Or rule 4 and use it with 2, that's how we got number 7. Okay, but they're important facts nonetheless. And they're going to come back and haunt us when we start doing problems. Okay, so I need to erase 7 and 8 for sure. Okay. Now, in my mind, I call these the intermediate log laws or log rules. Nobody calls them intermediate. That's just me. That's just my way of differentiating. Okay, these are pretty easy ones. I can handle these. These are a little bit nastier. Little bit nastier. Now, on that handout, the guy, okay, called it the product rule, and he is correct. He is correct. Okay. If you have the log base B of m times n. So look at what this says. if you have the log, and all this is everybody's got to be the same base of two things multiplying. You can split that into the log of the first thing added with the log of the second thing. So the log, okay, my words are going to sound really weird. They probably do anyway because it's math. But the single log of two things multiplying can be split into two logs that are adding. The single log of two things multiplying can be split up into two separate logs, okay, of the things adding. Okay, now there's a question, do log laws apply to ln's? Yeah. This could just as easily have been the ln of m times n, could be the ln of m plus the ln of n. Okay, it doesn't, a single ln of two things multiplying can be split into two separate ln's that are adding. Now, usually we don't put the log laws down twice because it's assumed that an ln is just a special log. So when I write log base b, I'm implying, they work for ln's also. They work for any base, and ln is just base e. So I'm going to erase this ln, but I'm going to give you a quickie example. He gave you one on the handout. So suppose you had log base 3 of 3x. Well, you can write that as the log base 3 of 3 plus the log base 3 of x. Okay, because what are the 3 and the x doing? They're multiplying together. Now, it just happens that, oh, look, log base 3 of 3 is 1. So this is 1 plus the log base 3 of x. So our using this product rule, the intermediate product rule, and one of these other rules, we could do a lot of simplifying of logarithmic statements. But that's the first, that's called the product rule, where you can split apart, okay, something that was multiplying. Now, I hate to burst your bubble, but this is called a bidirectional rule. Bidirectional. I should have written a double arrowhead here, because what it says is if you have two separate logs that are adding, you can condense them into one log that's multiplying. This is a bidirectional rule. Usually we think of it going in this direction from two, it splits from one big problem, it splits out into two little problems, but you could take the two little problems and put it into one big problem. And I'm going to give some examples of that in a minute. These are all bi-directional. They go forwards, they go backwards. The next law, the guy introduced, okay, he's got something called the quotient law. Excuse me. And that's if you had log base b of m divided by n. Okay. It is also a bidirectional law. It goes forwards and backwards, but you guys, with a little bit of thought, can come up with the answer yourself. Think about this. If two things multiplying can be split, excuse me, if the log of two things multiplying can be split into two separate logs that are adding, the log of two things multiplying can be split into two separate logs that are adding, then what happens if initially they're dividing?
They're minusing.
They're minusing. It's going to become the log base b of m minus the log base b of n. They're minusing. So in terms of brain power and memorizing, to me, these two are almost the same thing. Okay, if you memorize one and think about it, you automatically have the second one. So again, for memorizing rules, that's an easy one. Suppose you had log base 3 of 25 minus log base 3 of 5. Well, I'm looking at this going, well, wait a minute. Log base 3 of 25 minus log, they're both base 3, they're minus. I can convert this into log base 3 of 25 over 5. Two logs that are subtracting can be condensed into one big log that's dividing. But wait, the log base 25 over 5 is just 5. So this becomes log base 3 of just 5. So that's using this log law backwards. We took these two separate ones, condensed it into a single one, and then looked at that and said, well, it kind of simplifies a little bit more. So we did, and that's our final answer.
Good question. So
Yeah.
when you have those interchangeable roles, so log 3, base 3, 25 minus log 3, 5.
Base 3 or 5, yeah.
Yeah. Can you just minus it? Or you
Nope.
have to change it to division?
If you're going to minus it, then you have to use your calculator. You got to get the big ugly decimal here and the big ugly decimal here, and then subtract the two answers together.
Oh, okay. Okay.
Okay, you can't subtract logs like you're thinking of. They're not like terms where you could say, 5 logs take away 2 logs is 3 logs. It doesn't work that way. Logs don't work. They're weird. But you can condense it. And actually, let's go back. If you plug this in and got a big ugly decimal, and you plug this in and got another ugly decimal, and you subtracted the two as decimals, that would be the same as if you used your calculator on this. So the question is, a lot of these laws were developed and built because mathematicians are lazy. They're going, oh man, I don't want to worry about the decimals here and the decimals here. Okay, I don't want to, I don't want to say anything have to screw with my head. I'd rather use my log laws because it's easier down to one problem than to have two separate problems and a lot of stupid decimals. That's kind of the motivation. Okay, anybody else? Okay, the last one, what did he call it? He called it the power rule, which is good. So if you have log base b of m to a power, again, bidirectionally, you can bring that power in front. Okay. So basically what we say is the power moves out front and then multiplies the rest of the logarithm. So example of that, and again, it's bidirectional. If you've got a number out front and you want to, you can move it up as a power here. That's what that says. P was the power. So most common one is something like, what if you had log base 2 of x to the 4th power? Well, if it helps you, and see, that's always going to be a question. If it helps you, you can move the power out front, so it's 4 times log base 2 of x. Now, I don't know if that helps you or not, but that's what you're allowed to do. You're allowed to take this power and move it out in front, like I did here, and have it multiply the rest of the logarithm. Now, if we have time when we come back after the break, all of these rules are based on our exponent rules. And I'll show you why these are exponent rules. Okay, but right now I'm just asking you to accept these, practice with them, try and use them. And I'm going to show you how I'm going to test them. Okay, show you how I'm going to test them in just a second. So these are our basic rules here. And these are what I call the intermediate rules. This is the one that these are the 3 that most people remember. And then the real question is, well, how am I going to use them? So I need to erase this and to be able to put some problems up. Actually, you guys want to take about a 5-minute break? Okay. Nobody's beating down the door. We'll take a 5-minute break.
Yeah, we'll take a break.
Okay. Okay, we're back. A couple things. Just occurred to me that we have to do word problems tomorrow night also. And we'll have time, it'll be okay. But there's a word problem handout. I'm going to go over word problems, show you how to do them all. Okay, work on them tomorrow with logarithms and exponents. But if you want to download it so you can write on the worksheet along with me, that might help you. So I just made it available in Canvas in the chapter 10 of Canvas. So if you had an opportunity to download that, that would be great. It might help you tomorrow night when we do some word problems. So we're still in 10.4. We're still talking about the log laws, and we're going to use them in a lot of ways, but there's going to be 2 questions on the test. One is going to say expand. So I might give you something that looks like this. Log base 3 of 27 x to the 4th square root of y. And what I'm asking you to do is apply every stinking log law you can think of. Everything you can think of. Okay. So I'm going to show you on this particular one. Log base 3 of 27 x to the 4th times the square root of y. Well, the first thing I notice up here, I don't have my red pen. The first thing I notice is these are all multiplying. So what was that product rule? It said the log of a bunch of things multiplying can be separated into the log base 3 of 27 added with the log base 3 of x to the 4th added with the log base 3 of the square root of y. That would be a first step. Okay, again, go back and look at that product rule for logarithms. It said if you had the log of m times n multiplying, you can split it up into the log of m added with the log of n. Well, that rule works for as many things as you want to multiply. The log of m times n. Okay. Well, am I done? No, there's a trick here. Example. At this point, you should be seeing 27 as 3 to the 3rd. Again, logarithms are all about exponents. Plus log base 3 of x to the 4 plus log base 3 of y, check this out, to the 1/2 power. Okay, that's left over from chapter 9. Okay, and actually chapter 5. The square root of something is also the 1/2 power. Okay, well, why is that so darn important? Because we can move the powers in front. We can use that power rule for logarithms. Okay, so 27, you had to look inside of 27 to see that it was 3 to the 3rd power. That allowed you to bring the power out front. X to the 4th is kind of obvious. You can bring the 4 power out front, like I did here. Y to the 1/2, that's tricky. That's why I'm showing you this. The 1/2, the square root is the same as the 1/2 power. The square root is the 1/2 power, so I can bring the 1/2 power out. Okay, now there's one more step I can do. Here, I have a log base 3 of 3. That's worth 1. Remember, one of our log laws was a log base b of b is always worth 1. Log base b of b. So log base 3 of 3, this is 1. So your final answer for this problem is 3 plus 4 times the log base 3 of x plus 1/2 times the log base 3 of y. And that would be your final answer. And all you're doing is trying to show off that you recognize all the log laws that we can throw at you. So this is going to be a problem. Actually, in 10.4, Mom has a bunch of these. Okay. I will give you one of these on the exam and it will say expand. Something like this. Okay. Let's, any questions on that before I give you guys one to try on your own? All right. Then not enough room, but I want you to expand log base 5 of 125 x squared over y to the 3rd. Expand that, please. Sorry, so again, we had 125 times x squared. So those two expanded to a plus log of 125 plus the log of x squared. but the division expanded to a minus. So we have that. Okay. This, again, how you do your steps, the order, but this will become log base 5 of 5 to the third. 125 is 5 to the third, plus log base 5 of x to the second, minus log base 5 of y to the third. Okay. We can bring the power down. This is 3 times log base 5 of 5, plus 2 times log base 5 of x, minus 3 times log base 5 of y. And once again, log base 5 of 5 is worth 1. So final answer for this problem, 3 plus 2 log base 5 of x minus 3 log base 5 of y. And that is our final answer. Questions on either of these? Okay, well, these were expand. Okay, so what's the opposite of expand? Condense or contract. So these ask you to use your log laws to blow this thing apart. And again, just how much you're trying to impress me. How many log laws do you think you can apply to this? Well, we're going to reverse the idea. I'm going to say condense. Okay, mom says write as single logarithm. Okay, I say condense. If we expand, we can condense. Mom says not condense, but write as a single logarithm. Easy example. 2 times the log base 5 of 7 plus 1/2 times the log base 5 of x minus the log base 5 of y. Okay, so I'm going to walk you through this. Okay, first thing I see is I can do my power rule. So this becomes the log base 5 of 7 squared plus log base 5 of x to the 1/2 minus log base 5 of y. So, okay, hang on. I'm going to do this in separate steps. Most people don't bother. I'm going to do the first two. 2 separate logs that are adding can be condensed into 1 log that's dividing 49 over the square root of x. Okay. No, come on, Foster. I said that totally wrong. Erase that, edit that out of my video. I'm thinking a step ahead. I'm thinking actually the next problem. I beg your pardon. This is log base 5 of 49 times the square root of x. I'm sorry. Jeez. Okay. Minus log base 5 of base 5 of y. Okay. So 2 separate logs that are subtracting becomes 1 log that's dividing. Okay. Now, the game is once you've moved the power up, most people will just say, oh, when I'm condensing them, the positive logs show up in the numerator and the negative log shows up in the denominator. Most people don't do it by 2 or 3 different steps. Once you're at this point, they just say, if they were positive, if they were adding, then they show up in the numerator. 7 squared is 49 in the numerator. X to the 1/2 is the same as the square root of x in the numerator. Those were adding, so they stay in the numerator. But because this was subtracting, that means division, so it will show up in the denominator. Again, whether you do it in 1 step or 2 steps or 3 steps, okay, that's the correct answer. Okay or not okay? Notice the instructions. I say condense, bring it all together. Mom says write it as a single logarithm. So instead of 3 separate logs, you brought it into one big giant log. Questions? All right, you guys try this one on your own then. Log 3 log base 7 of 2 minus log base 7 of 4 minus log base 7 of x. That will cause you some headache. And do the power rule and then look to cheat, or at least shortcut. So take a second, think about that one. Okay, so if we started this, log base 7 of 2 to the 3rd power minus log base 7 of 4 minus log base 7 of x, bringing the power in. Now, if we did it step at a time, okay, actually, well, I don't want to say don't copy this, but this is going to be wrong, or rather, it's going to lead us into a dead end. This is going to be log base 7 of 8 over 4 minus log base 7 of x. Now, 2 to the 3rd is 8. Now, suppose you didn't know that 8 and 4 reduce. Okay, suppose you didn't. Then you might write this log base 7 of 8 over 4 over the x. Okay, and while you're not wrong, you're not correct either. We, as mathematicians, math teachers, hate complex fractions in our answer. We want the fraction to have one nice numerator, one nice denominator. That's the end of it. So this fraction over another fraction stuff, we hate. Okay. Now this particular one, the 8 and the 4 happen to reduce. Okay. And so we maybe got lucky, but that won't always be the case. So I want to show you an alternate way of doing this problem. Remember what I said over here. I said if they were adding, they usually always showed up in the numerator. And if they were subtracting, they showed up in the denominator. Well, the same thing is going to apply here. Okay. The log base 7, the 2 cubed is going to show up in the numerator because it was a positive. But these two are going to show up in the denominator. That's a shortcut. That's a trick. But it saves you so much headache. Okay. Shortcut, trick, yes. Okay. A positive number will show up in the numerator. It did. 2 to the 3rd power was 8 in the numerator. These were both minuses. They will show up in the denominator, 4x. You're condensing. Remember, you're bringing them, you're bringing them together. Now, this happens to reduce. So you can say this is log base 7 of 2 over x, which is the same answer I had when I tried it the first time. But that's because there was some nice, pretty reducing. That won't always be the case. So anyway, Mom will give you a lot of practice on these. On the actual exam number 3, I will have 2 problems. One problem that says condense, one problem that says expand. That's it. One condense, one expand, just like these. Questions? Okay, now I want to move in a little bit into 8.5, just a little bit. We won't be able to finish it all tonight anyway. There's so much there. And the reason I want to get there is because we've talked a lot about section 8.5, which is solving equations. Okay, we've talked about them. We just haven't talked about them officially yet. So I need to erase this so I can move into 8.5. We'll review and continue 8.5 tomorrow also, so don't panic too much. Can I erase? Anybody gonna scream at me? Okay. Chapter 8.5. No, not 8.5, 10.5. Okay, it's about my bedtime. I'm losing it. Okay, is about solving either exponential or logarithmic equations. Okay. And tonight, I want to focus on exponential equations. Tomorrow night, we'll worry about logarithmic equations and word problems. Okay, but tonight, exponentials. So the first exponential is same base. And we've already talked about that. That was something we did our very first night. For example, if you had 5x plus 2 times 25 to the 3x minus 7 equals 1/5 to the x minus 9. Now I'm going to walk you through this, okay? But this is a fair question to put on exam number 3, because we've gone over it and over it. Okay, what you're supposed to do is look into all of these and say, okay, can they all be turned into the same base? Yeah, 5. So this is 5 to the x plus 2, times 5 squared to the 3x minus 7 equals, now this is where it got tricky, 5 to the negative 1 to the x minus 9. To flip over the 1/5, you have to introduce the negative 1. Okay, way back in chapter 3 or 4, if we had 5 to the negative 1, you would say, oh, that's 1/5. Okay, well, we're reversing that. If you have 1/5, that's 5 to the negative 1. But the key is we have to have them as all 5s, base 5. So this is 5 to the x plus 2 times 5, power to a power you multiply, 6x minus 14 equals 5 to the negative x plus 9. A power to a power you multiply. Now, the next thing we want to do here is it had to be a single base 5 on this side and a single base 5 on this side. Just because we have all base 5, that's not good enough. We have to condense these into one base 5. And so the way we did that is we said this is 5 to the 7x minus 12 equals 5 to the negative x plus 9. If we had 5 to the 3 times 5 to the 9, the rule would say we would keep the base 5, add the powers 3 plus 9. Well, that's all I did here. 5 to some power times 5 to some power, keep the base, and I added the two powers together. X plus 2 plus 6x minus 14 combined like terms. Okay. Once they're the same single base, same single base, 5 and 5, and there's 1 5 on each side. 5 here, one of them. 5 here, one of them. We can drop the 5, and that becomes 7x minus 12 equals negative x plus 9. Finish, I don't know what that is. 8x is 21, I think. So x is 21 over 8. And that's our answer. So, in section 10.5, they will have a few problems like that. There will be a couple of these, not too many, on the exam. But these were called, this is called exponential equation, because it was exponents, and they were same base. Now, what if we did something like this, different base? Unfortunately, there's two ways that these problems can be done. Two ways. Okay, let's start. 5 to the 2x plus 3 equals 79. Actually, there's about 4 ways. Holy crud. It's going to get really hairy tonight, guys. I hope you haven't fallen asleep. Now, we just spent earlier this evening talking about the Brabar Rule. Okay, 5 to the 79. Okay, was that log base 5 of 79 equals 2x plus 3. Okay, the definition of logarithms allows us to convert this exponential equation into a logarithmic equation. And now we could just use our calculator. So turn it on, clear. Log base 5 of 79, boom. So I get 2.71489 equals 2x plus 3. The rest of this I'm going to do on my calculator. I'm going to take away 3 and then divide by 2. And I get negative 0.14255 is approximately x. Again, pay attention to the directions, what they're going to tell you to round to. Usually it's 4 decimal places. So in this case, it'd be negative 0.1426 if we rounded to 4 decimal places. Now, that's one way. The other way that is commonly taught, same problem. Okay, is people take the ln of both sides. So they write the ln of 5 to the 2x plus 3 equals the ln of 79. Okay, notice it's the same problem. We have to get the same answer. Have to. But we're using alternate techniques. As long as you show me your steps, I will give you full credit. Okay, because both of these are acceptable. In fact, tomorrow I may show you a third way, but why is this so good? Why would somebody say, oh, okay, you can take the ln on both sides? Who cares? Because of that power rule, we're allowed to bring the power out front. So this becomes 2x plus 3 times the ln of 5 equals the ln of 79. By taking the ln of both sides, that opens your problem up to being able to use all those log laws that we just discussed earlier tonight. Okay, and the main one here is it allows us to take that power out front, which I did. But then we're going to divide both sides by the ln of 5, and we're going to get 2x plus 3 equals this mess. Okay, now at this point, if you do the rest of it on your calculator, I get 2x plus 3 equals 2.71489, et cetera, Notice that the problems at this point are exactly the same. So it kind of depends on what your instructor, might be a chem teacher, might be somebody else. A lot of people like to use this technique, ln of both sides, allowing you to use your log laws. Other people like to use the Brabar technique, convert it instantly into a logarithmic equation, and then use your calculator. Both of these are identical to each other. And I personally don't care which technique you use. Okay. Like I said, there is a third way, but I'm not going to worry about that one right now. You guys want to try? Well, we've done these tonight. We've done these. I may do a few more, but I want to show you the real power of this before we go. Okay. One of the main keys that I keep pushing, but probably not enough. Suppose you had 5e times e to the 2x plus 1, let's say minus 1, I don't know, equals, I don't know, 35. Oh, 350 will be fun. And I'm going to ask you to solve that. Well, one of the themes that we've always done is before we attack the exponential, we isolate it. Think about that. When we had 5 minus 2 absolute value x plus 3 equals, I don't know, 17, negative 17. Before we split the absolute value, we had to get it all by itself. Remember that? So absolute value of x plus 3 equals 11. Then we could split it up. That was one of the key ideas. Every time we had a weird math function, operation, rule, whatever you want to call it, before we did what we were supposed to do, we got it isolated. Okay, same thing was true. Okay, 2 plus 3 times the square root of 5x minus 1 equals 15, 14. That'll work. Equals 14. Now we know that the only way to get rid of the square root is with the square power, but you were supposed to isolate it. So the first thing you did was take 2 away from both sides. That gave you 3 times the square root of 5x minus 1 equals 12. And then you divided both sides by 3. And you got the square root of 5x minus 1 equals 4. Now that you've isolated the weird thing, the square root, now you can square both sides and finish off the problem. Okay. So my point was, whenever we had something weird, isolate it first. Okay. Well, let's see what happens. The first thing I'm going to do is divide by 5. That gives me e to the 2x minus 1 equals 70. Okay, there's 2 ways this problem can be done. First way, Brabar. Okay, that's the method I'm going to use here, the Brabar method. Okay, log base e of 70 equals 2x minus 1. But this has a little trick. What is log base e the same as? Again, I know it's new. It was one of those log laws. When you have log base e, it's the same as the ln of 70 equals 2x minus 1. So the phrase log base e turns into ln. So log base e of 70 becomes the ln of 70. And now this is just calculator stuff. So the ln of 70 is something, I don't know, 4 point whatever. I'm going to add 1 to both sides. Then I'm going to divide by 2. And I'm going to get 2.624247 is approximately X. And again, whatever we round to, whatever it says. Okay, so that's utilizing learning that we already know. Okay, just say, okay, I have no idea how to do this. It's an exponential, but if I use the Brabar rule, then I know I can switch it and everything will work out nice. I know I can do that in my calculator. Okay, alternate way. Remember what I did over here? I took the ln of both sides. So if I take the same problem and I take the ln of both sides, so the ln of e to the 2x minus 1 equals the ln of 70. Okay, once I've introduced the ln, remember an ln is just a logarithm. It's a special logarithm, but it allows me to bring the power out front. So this is 2x minus 1 times the ln of e equals the ln of 70. Okay, here's the magic. Okay, I'm not going to skip a step. This is 2x minus 1 times, what does ln of e stand for? Well, it is log base e of e. But we just figured out way back at the beginning of the night that that is 1. So this becomes 2x minus 1 times 1 equals the ln of 70. And notice right there, that problem, okay, which I conveniently put into the glare. Very good, Foster. Couldn't have planned it better if you tried. Okay, that problem right there is exactly the same as that problem there. So we're going to get the same answer. So again, 2 ways to do this. This problem was isolate the weird thing first, the exponential in this case. Study the exponential. Ask, how in the heck do I do it? 2 ways. One is to apply the Brabar rule, turn it from exponential to logarithmic, and turn the log base e into ln. So eventually you have to use that rule. The alternate way to do this same problem was to take the ln of both sides, just like I did over here, the ln of both sides. Okay, well, that allows me to bring the power down. But the beauty of this is that the ln of e becomes 1. So it effectively drops out of the problem. Okay, and then you have this same step. Again, these are in 10.5. You should be able to try a few of those, whatever. Tomorrow night, you're bringing at least the 3 worksheets. You're bringing the log law worksheet, you're bringing the how to solve worksheet, and you're going to try and bring the word problem worksheet. And we're going to go through all of those. So see you tomorrow night. Bye-bye, guys. Hasta bye-bye.
Thank you.
Bye-bye. Oh, yeah.